Let's see how the cipher systems would actually work. So to begin with, we have to define some terms. First of all, we are going to talk about an symmetric cipher system. Now, there's also something called an asymmetric cipher or a public key cipher system, but we will come back to that later to see how it works. An asymmetric cipher is built on the same ideas as the symmetric cipher system, so let's look at the symmetric version first. So we have a couple of terms here. First of all, we will talk about messages, and we're going to be denoting messages with a lowercase m. We have keys or cipher keys, which we will denote with a lowercase k. And we have cipher texts denoted with a lowercase c. And with a cipher, what I specifically mean is a pair of algorithms that deal with encrypting and decrypting data. These cipher suites are usually defined over three possible spaces of values. So there's the space of all possible keys, the space of all possible messages, and the space of all possible cipher texts. So let's look at these two black boxes that somehow encrypt and decrypt data once more. So on the left, the message M goes into the box for encrypting data. We also need a key that we have somehow generated. And if you put a key and a message into this encryption box, a ciphered version of the original message comes out. If we then put the resulting cipher text and this same original key into the decryption box, the box will output the original message back. This is why we say it's a symmetric encryption system. You start off with one message and one key, and if your encryption and decryption systems work properly, you will be able to extract the same message at the end of this pipeline. And that's basically what these boxes in the picture mean. So we probably have an idea of what the messages could be. A message could be something simple like "Hello world" or "Mom, please send me more money." But what could the keys possibly be? Well, to answer that, let's look at a few historic encryption schemes to figure out how the keys could work. A classic, really old encryption scheme is what is known as a substitution cipher, or sometimes called the Caesar's cipher. So the key is basically a chart of how to map individual letters of the alphabet. So in this case, the letter A always corresponds with the letter C. B becomes a W, C becomes an H, and so on. And the point is that there is a mapping for all the possible letters in the alphabet. So for example, if we use this sort of substitution cipher, we would formalize this as a formula like shown here on the left. So the encryption for this particular message uses the key mapping K and a custom message. So the encryption formula would have these as the parameters for the transformation. The decryption formula would work similarly, again using this same key mapping. Now this is a very simple cipher system for one reason, that is because, well, if we think about it, there's 26 letters in the English language. So our key space that we could possibly pick a key to cipher our message, that key space would be something like 26 factorial, because there's a limited number of ways that we could use to arrange this letter mapping. So in other words, there is a limited number of ways that we can arrange the alphabet in our key table. That also means that it's relatively easy to break a substitution cipher. if we see a message that has been encrypted using a substitution cipher, all we have to do is basically figure out the letter frequencies used in the language that the text was written in. So, for instance, the most common letter in the English language would be E. So probably most of the letters that you see, especially in a long message, if you see a letter appearing many times, probably it's an E, as it is the most common letter. A is the third most common letter, and so on and so on. Also, you can use the information about frequencies of pairs of letters. Pairs of letters are called bigrams. If you take into consideration this kind of substitution, you would probably be able to figure out at least parts of the original message just by looking at the ciphered message. What that means is that a substitution cipher is vulnerable to what is called a ciphertext-only attack. So ciphertext-only means that you only need to look at the ciphertext and you will be able to figure out what the original message was. There is a variation of the substitution cipher called the Visionnaire Cipher. This variation basically improved the security of the substitution cipher at least a little bit. The Visionnaire Cipher was actually the first cipher in history which uses some sort of key to encrypt your message. So let's say we had a message that's going to be attack at dawn. Then we have a key that's going to be lemon. And now we use this key to produce some ciphertext. First of all, we have to pad out this key to be as long as the original message. Then we're going to do a little mathematical operation of counting together the letters in the original message and the letters in the keyword. This mathematical operation is a simple addition. So for instance, A plus B would produce C. So you add together the first and the second letter of the alphabet, and as a result you get the third letter. If you hit the end of the alphabet or run out of letters, then you return to A again. This is what is called modular arithmetic. Decryption works the same way, but in reverse. The Visionnaire Cipher is historically important because it introduces the same idea that symmetric encryption uses to this date. This idea is that it's the key that matters. The key and the message together produce this substitution. Sadly, the Visionnaire Cipher is not infallible either. But it is slightly more hard to break by hand, but if you can use a computer, it takes about 2 seconds to figure out. All you have to do is try out all the possible substitutions and then do a frequency analysis, and you will be able to see patterns and frequencies in the text and break it just like the substitution cipher. The third most significant technological advance in ciphers is another variant of the substitution cipher. This almost worked flawlessly, so this is what is called the Hayburn Machine or a rotor machine. Probably the most famous rotor machine was the German Enigma in the Second World War. So what this does is effectively a substitution cipher, but it has many substitution tables. Basically, it's this machine where the input message is put through a series of substitutions, and these substitutions are determined by the positions of a series of rotors which have been joined together. These rotors move after each substitution, producing the next series of substitutions. In the Enigma, there's 3 different substitutions that happen one after another, and to make things even more complicated, you would use 3 rotors that were selected out of a possible of 5. This makes the key space roughly equivalent to about 2 to the power of 18. In certain branches of the German military, an additional layer of substitutions was also added using a plug board, which changed certain letters to another. The Enigma machine was not infallible either. although it only had one little mistake in its design. If you're interested in that sort of thing, you can probably Google for what that mistake was, and I will leave it as an exercise to the listener to figure out what the fatal flaw in the Enigma encryption was. Now that we understand the evolution of the different ciphers and how messages are transformed into ciphertexts, let's look at the terms and definition of encryption once again. So again, we divide the cipher suites into symmetric and asymmetric ciphers. This is going to be important later on, but for now we will talk about symmetric ciphers first. So the encryption algorithm takes in the plaintext message and the key and produces a ciphertext. The decryption algorithm takes in a key and the ciphertext and produces the original plaintext message. Asymmetric ciphers are almost identical except with one difference. To encrypt and decrypt, you actually need two different keys, one for encrypting and one for decrypting. Most important here is that the encryption key cannot later on be used for decryption of the message. A cipher is defined as the pair of two efficient algorithms, E and D, where E is the encryption algorithm and D is the decryption algorithm. Then there is a formula here. This is what is called the consistency formula for ciphers. Basically what it means is for all possible messages and all possible keys, if you encrypt any individual message with some pre-selected key and then proceed to decrypt the resulting ciphertext with the same key, the original message must come out. So basically what this formula is saying is if you encrypt something using a key and then you decrypt the ciphertext using the same key, the original message better come out, because otherwise your cipher system is fundamentally flawed. You would not be able to decrypt your own secret messages. Something to maybe remember for future use is that encryption often uses randomization to produce a different outcome each time. But the decryption should always be deterministic. That's again to remind of this formula. So encryption needs to be more or less random so that it's hard for an outsider to guess what the original message might be just from the ciphertext. But the decryption needs to be deterministic because we have to produce the original message back. But that's just a little food for thought for later use.